In this video, we're going to see an example of a natural transformation between contravariant functors. And in particular, we're going to see that there's a natural transformation between the contravariant Hom functors of a category. So let's recall the definition of a contravariant Hom functor. So take a category C and fix some object A in our category C. Then we can denote the contravariant Hom functor for that object A as Hom blank A, which goes from our category C to the category of sets, such that we map objects C in C to Hom sets going from that object C to our fixed object A. So you can see that in some sense A can be thought of as the target object for this functor, because all objects are getting mapped into a bunch of morphisms which all land in A. And we also need to map the morphisms, so we map morphisms F from C to D to the preceed by F function, where the preceed by F function takes morphisms from D to A and simply just precedes by F. So we apply D after F, which, as required, is a morphism in the Hom set from C to A. F takes us from C to D, D takes us from D to A, so D after F will take us from A, C to A. So what would it mean to have a natural transformation between two contravariant Hom functors of a category? Well, let's say we have the contravariant Hom functor Hom blank A, and let's say we also have the contravariant Hom functor Hom blank B. And let's say A and B are both objects in a category C. Then our Hom functors go to the category of sets according to if we have a morphism F going from an object C to an object D in our category C, then since it's contravariant, we're going to be mapping the object C to this object, which is going to be the Hom set from C to A. D is going to be on this side and is going to get mapped to the Hom set from D to A. And our morphism F is going to get mapped to the preceed by F function. Of course, we'll have the same thing on this side. So our morphism F will get mapped to preceed by F, which will go, in this case, from the Hom set from D to B this time, with this functor, to the Hom set from C to B, and again this will be preceed by F. So what would it mean to have a natural transformation between these two contravariant Hom functors? Well, it would need to be a collection of functions going from Hom set D to A, for example, to Hom set D to B, and from C to A going from the Hom set to C of B, where we might call this lambda D and we might call this lambda C. And therefore, the condition that we would need to have for us to have a natural transformation would be that these two chains commute. So lambda C after preceed by F this chain, would commute with this chain, precede by f after lambda d. Now we're in the category of sets here, so both of these chains are set functions, and they're applied to the domain, which is the home set from D to A. So what this really means is that if we take any morphism D from D to A in the category C, then we need to have that lambda C after precede by F applied to D is equal to precede by F after lambda D applied to D. So if we were to have a natural transformation between these functors, the domains for each one of the functions in that natural transformation would be morphisms, which all go from some object C to our object A, our fixed object A for the functor. And also notice that all of those morphisms are in C, since all of these home sets come from our category C. So what we could try is we could redraw this diagram, but instead of using an arbitrary morphism F from C to D, we could use one of the morphisms in one of these home sets, because all of those morphisms are also in C. So let's try that. So let's take some arbitrary object C and C, and we're looking at the home set from C to A in that case. So let's take a morphism F from C to A this time. Well, then our morphism F from C to A, here by the contravariant Hom functor with target A, home blank A, we will map F to precede by F. But in this case, we're going to go from the home set from A to A, we fill in the blank with A, to the home set from C to A, fill in the blank with C, and it's a contravariant functor. And of course, the same applies for the contravariant Hom functor with target B, home blank B. We have precede by F, but this time it goes from the home set from A to B to the home set from C to B. So again, if this natural transformation exists, then we must have, in this case, that lambda C after precede by F is equal to precede by F after lambda A in this case. But notice that the domain for both of these chains is the home set from A to A. And we know that in the home set from A to A, we must have the identity on A. So that is, this equation must also hold, if there's a natural transformation, when we apply it to the identity transformation on A, which would look like this. So now we can apply precede by on both sides to get lambda C of 1A after F is equal to lambda A 1A after F. And in this case, this is just lambda C of F. And on this side, we can kind of flip it. So instead of precede by F, we can think of it as follow by lambda A 1A applied to F. But this F was just an arbitrary morphism from C to A. And so this will apply in general, which is that lambda C is equal to follow by lambda A 1A. But not only that, this object C was also arbitrary, and so this pattern will apply for any object C. And so we get that if there's a natural transformation between these contravariant Hom functors, lambda, then it has to just be lambda A 1A followed by applied to each of the different domains, which are home sets landing in A. So if there is a natural transformation between these contravariant Hom functors, we know exactly what it needs to look like. It needs to satisfy this. However, we don't actually know if this is a natural transformation. We need to confirm that this is actually a natural transformation between these contravariant Hom functors. So how can we check whether or not this is a natural transformation? Well, the first thing to note is that in general, lambda A could assign the identity on A to any of the morphisms in the Hom set from A to B. So we know that lambda A maps morphisms in the Hom set from A to the Hom set from A to B. And so we know that in general, 1A could get assigned anything in the Hom set from A to B. But if we do assign it, let's say there's some B in the Hom set from A to B that lambda A 1A maps to, then that completely determines the natural transformation for that element. And we could do that for any of the elements in the Hom set from A to B. So in some sense, there's one natural transformation possible for each element of the Hom set from A to B, call them B. So we need to check that preceed by B for any of the morphisms in the Hom set from A to B can commute with preceed by F. So we can go back to our natural transformation graphic for a general morphism, any morphism in the category C, because of course this natural transformation commutativity property needs to work for any morphism, not just morphisms landing in A, as we were looking at before. Again, we have set on this side. And if we fix some B, some morphism B going from A to B in the category C, then we need to check whether or not follow by B applied to any domain in the image under the contravariant Hom functor will give us the commutativity property that we need for a natural transformation. That is, we need to see whether or not B after preceed by F is equal to preceed by F after followed by B. So then let's take some G in the Hom set from D to A, and let's apply the left side to that G going from D to A. Well, this is equal to followed by B applied to G after F, which is the same as B after G after F, which is the same thing as preceed by F of B after G, which is the same thing as preceed by F after followed by B applied to G. So we can see that QED, we have satisfied this commutativity property, which means that we do have a natural transformation going between covariant Hom functors, Hom blank A and Hom blank B, where all we need to do is fix a morphism going from A to B, and that completely determines a natural transformation by applying follow by. So to recap our discussion, anytime we have two contravariant Hom functors, call them Hom blank A and Hom blank B, we can create a natural transformation between them by simply fixing any element B in the home set from A to B, that is a morphism going from A to B, and then taking the collection of all the follow by B functions defined on any of the home sets going into A. So if you have any home set going from any object C into our fixed object A for the first functor, then you take all of the follow by B functions defined on all of those home sets, then this will create a natural transformation. And so what this means is that there is one natural transformation for every element B in the home set from A to B, and moreover, those are the only ones possible. So we can count exactly the number of natural transformations between Hom functors. One good exercise to try would be to remember the covariant Hom functor. That is, a morphism F from C to D gets mapped to the follow by F function from the home set from A to C to the home set from A to D, and similarly for a different covariant Hom functor, Hom B blank, we have preceed by F between the same two. And the question would be, is there a natural transformation that goes between the covariant versions of the Hom functor? And you can try to follow a similar argument that we made earlier in the video.